Imagine standing under a pitch-black sky and trying to count every galaxy in existence. If you counted just one every single second, never stopping to eat or sleep, you would be counting for 63,000 years. That is nearly 10 times longer than all of recorded human history. Does it make you wonder how small we truly are in this infinite ocean of light, and what secrets remain hidden in the darkness, where even our strongest telescopes cannot see? Astronomers now estimate there are 2 trillion galaxies in the observable universe. To visualize that, imagine a 2 followed by 12 zeros. But here is the most staggering realization: 90% of those worlds are completely invisible to us. They are too faint, too small, or too far away for our current technology to detect. Everything you can see with the naked eye on a clear night, every star, and even the faint glow of the Andromeda Galaxy, is just an unimaginably tiny fraction of what actually exists out there. This massive number of 2 trillion only accounts for the part of the cosmos where light has had enough time to reach us since the beginning of time. Beyond that boundary lies even more of the universe, perhaps hidden from our instruments forever. Today, we begin a journey to find them. We will explore the scientific path that led us from earlier estimates of 100 billion galaxies to the staggering 2 trillion we recognize today. We will investigate the cosmic web, a breathtaking structure that connects everything across impossible distances, and we will search for the hidden majority, the countless galaxies swirling through the dark that we are only just beginning to understand. Make yourself comfortable. This is a journey through the deepest questions we have ever asked about the cosmos. Before we can truly count the galaxies, we must understand what it is we are actually measuring. The answer is far less straightforward than you might expect. At its core, a galaxy is a collection of stars, gas, dust, and dark matter, all bound together by the invisible hand of gravity. While that sounds simple, the sheer variety of these cosmic islands is breathtaking. Take our home, the Milky Way, for example. It houses anywhere between 100 billion and 400 billion stars. The fact that we cannot provide an exact number reveals the massive challenge astronomers face. Many of these stars are hidden behind thick clouds of gas, or simply shine too faintly to be seen. Furthermore, because we are located deep inside the Milky Way, trying to map it is like standing in the middle of a dense forest and trying to count every single tree while the trunks in every direction block your view. The scale of our galaxy is difficult to wrap the mind around. The Milky Way spans about 100,000 light-years. If you were to drive a car at highway speeds from one edge to the other, the journey would take roughly 670 billion years. Yet, compared to others, our galaxy is merely average. There are giants that cast the Milky Way into a total shadow. Consider IC1101, a supermassive elliptical galaxy. Recent studies estimate its diameter to be between 400,000 and 550,000 light-years, meaning several Milky Ways could fit side by side inside it. It contains an estimated 100 trillion stars, which is about 1,000 times more than our own galaxy. At the opposite end of the spectrum, we find the dwarf galaxies. These are the smallest members of the cosmic family, yet they are the most common inhabitants of the universe. An example is Segue 2, a tiny dwarf galaxy orbiting the Milky Way that contains only about 1,000 stars. There may be more houses in your neighborhood than there are stars in that entire galaxy. It is so small and faint that it was not even discovered until the year 2009. This is a crucial point for our count when astronomers speak of 2 trillion galaxies. A vast portion of that number consists of tiny dwarfs like Segue 2. These are not magnificent spirals, but often just modest clusters of a few thousand stars scattered across the vast ocean of the universe. To understand why counting the universe is such a monumental challenge, we must first look at the diverse forms these cosmic islands take. Galaxies are not all uniform. They are shaped by billions of years of gravitational interactions and stellar evolution. We begin with the spiral galaxies, the classic image that most often comes to mind. These consist of a bright core of ancient stars surrounded by elegant, sweeping arms filled with gas, dust, and brilliant young blue stars. Both our Milky Way and the Andromeda Galaxy belong to this category, which accounts for approximately 60 to 70% of the large galaxies we can observe. Then, there are the elliptical galaxies. Their shapes range from nearly perfect circles to elongated forms resembling a football. These systems are mostly populated by older, reddish stars and contain very little of the raw material needed to birth new ones. They cover the entire scale of the cosmos, from the smallest known systems to the absolute titans, like IC1101. Between these two extremes lie the lenticular galaxies. They possess a flat disk, like a spiral, but lack the distinct arms. You can think of them as spirals that have exhausted their gas supply and are now slowly fading into the darkness. Finally, we find the irregular galaxies, which follow no specific pattern. Their chaotic shapes are often the result of the immense gravitational pull from neighboring galaxies, with the Magellanic Clouds visible from the southern hemisphere being the most famous examples. However, this is where the true challenge for astronomy begins. Where exactly do we draw the line? Consider globular clusters, which are dense groups of millions of stars. The Milky Way alone has about 150 of them. Are they galaxies? Most experts say no because they lack dark matter. Yet the dividing line remains frustratingly blurry. Even more mysterious are the ultra-diffuse galaxies. These are the true ghosts of our universe. They can be as large as the Milky Way but contain so few stars that they appear almost invisible to our instruments. Some are composed of 99% dark matter. We do include these in our count, but their existence highlights a profound truth. The number of 2 trillion galaxies is not a simple tally, like counting marbles in a jar. It is a calculation based on deep assumptions, complex definitions, and objects that sit right at the edge of what we can imagine. For decades, astronomers operated under the belief that between 100 billion and 200 billion galaxies inhabited the observable universe. However, in the year 2016, that estimate suddenly increased tenfold. To understand how this happened, we must travel back to the year 1995, to a daring gamble that changed astronomy forever. At that time, researchers made a decision that many of their peers considered reckless. They pointed the Hubble Space Telescope at a tiny, seemingly empty patch of the sky and simply stared. For 10 days, the telescope collected light from a region that appeared absolutely pitch black. This slice of the heavens was incredibly small. If you held a 10-cent coin at arm's length against the night sky, the area being observed was roughly the size of Franklin Roosevelt's eye on that coin. This tiny speck represented only 1/24 of the entire sky. Many astronomers argued this was a waste of precious telescope time, as Hubble was one of the most sought-after scientific instruments in the world, and they were dedicating 10 full days to nothing. But when the data finally returned, the scientific community was stunned. That microscopic point of darkness actually contained approximately 3,000 galaxies. These were galaxies in a region so small, you would need a powerful magnifying glass just to see the area on a piece of paper. Some of these worlds were so distant that their light had been traveling toward us for over 10 billion years. This image became known as the Hubble Deep Field, and it fundamentally reshaped our understanding of the cosmos. If this random, tiny sliver held 3,000 galaxies, and the entire sky consists of 24 million such sections, the mathematical conclusion was overwhelming. By multiplying these numbers, scientists reached an initial sum of roughly 70 billion galaxies. In the years 2003 and 2004, Hubble looked even deeper into the void with the ultra-deep field. In a region measuring only 1/13 of the diameter of a full moon, 10,000 galaxies became visible. Based on this, science accepted an estimate of 100 billion to 200 billion galaxies for many years. Yet, a fundamental problem remained hidden behind these figures. We were only counting the galaxies we could actually see. Behind the impressive numbers we have discussed so far lies a fundamental problem that for years kept our understanding of the universe incomplete. We were counting only the galaxies that we could actually detect directly with our technology. Imagine for a moment that you are a fisherman trying to determine the total population of the ocean by using a net. If the holes in your net are too large, the majority of the fish will simply swim through them, leaving you with a count that is tragically low. If 90% of the sea creatures are too small for your mesh, your entire estimate of life beneath the waves will be wrong. This is exactly what happened to astronomers as they tried to tally the galaxies in our sky. In the year 2016, A groundbreaking study, led by Christopher Consolis, changed everything. His team did not necessarily discover new galaxies through a lens. Instead, they used sophisticated mathematical models to analyze how the number of galaxies has shifted across the different epochs of cosmic history. Because light takes a significant amount of time to travel through the vastness of space, looking at distant galaxies is the same as looking back into the past. The results of this analysis were truly startling. The early universe was much more densely populated with galaxies than the cosmos we see today. Back then, the universe was filled with an almost countless number of small dwarf galaxies. Over the course of eons, these tiny systems collided and merged with one another to form the larger structures we recognize now. Even our own Milky Way was born from these ancient, violent mergers. When we use mathematics to account for all those galaxies that must have existed based on these cosmic growth rates, the number skyrockets. The current estimate is staggering 2 trillion galaxies in the observable universe. This is 10 times higher than the previous value we held as scientific truth. It means that the 100 billion to 200 billion galaxies we previously talked about were only the ones bright enough to be seen directly. 90% of the galaxies in existence remain invisible to our telescopes, hidden as faint and small flickers deep in the distant reaches of space. To truly grasp the weight of this, we must define a term we have used several times without fully explaining its haunting significance: the observable universe. It is time to look closely at this concept, as it is one of the most fundamental principles in all of cosmology. When we speak of the observable universe, we are not talking about the entire cosmos. We are only describing the small fraction that we are physically able to see. The reason we are limited to this fraction has nothing to do with how powerful our telescopes might become. Instead, it is rooted in the very nature of light and time itself. Light moves at a finite speed of approximately 186,000 miles per second. By everyday human standards, this is unimaginably fast. At this speed, light could circle our entire planet roughly 7.5 times in a single second. However, the universe is so vast that even at this extreme pace, light requires a significant amount of time to cross meaningful distances. Because of this delay, when we look up at the sky, we are always looking into the past. The light from our sun takes about 8 minutes to reach us. If you look at the nearest star after the sun, Proxima Centauri, you are seeing light that was sent out about 4 years ago. When we observe Andromeda, our nearest large galactic neighbor, we are looking 2 million years into the past. This means we never see galaxies as they are today. We only see them as they were when their light began its long journey toward our eyes. Now, we must consider a decisive fact: the universe has not existed forever. It had a beginning approximately 13.8 billion years ago, in the event we call the Big Bang. This means light has only had a limited amount of time to travel through space. You might assume that we can see objects up to a distance of 13.8 billion light-years, as that is the distance light could have traveled since the start of everything. But the reality is far more complex because the universe is expanding. Space itself is constantly stretching. Galaxies move away from each other, not because they are traveling through space, but because the space between them is literally growing. This expansion causes the light from distant objects to be stretched as it travels. It also means that those far-off galaxies whose light finally reaches us today are now much further away than they were when they first sent that light out. When we factor this expansion into our calculations, we find that the observable universe actually has a diameter of about 93 billion light-years. Everything beyond this limit, which we call the cosmic horizon, remains invisible to us. This is not because there is nothing there, but simply because there has not been enough time since the dawn of the universe for light from those distant regions to ever reach us. We are truly like islanders looking out at a sea, knowing more land exists just beyond the curve of the world, forever out of reach. The realization that we are limited by a cosmic horizon leads us to a truly dizzying conclusion. The universe almost certainly exists far beyond the boundaries of what we can see. Most cosmological models suggest that the entirety of the cosmos is many times larger than the observable fraction we have mapped so far. Some estimates propose that the total universe could be at least 250 times larger in diameter than the part visible to our instruments. Other theories take this even further, suggesting the universe might be infinite in its reach, because we are, by definition, unable to look past our own horizon. These ideas remain hypotheses, yet they radically expand our perspective on the true number of galaxies. When we state that there are approximately 2 trillion galaxies in the observable universe, we are only counting those within our specific cosmic horizon. If the universe is built uniformly in all directions, a concept supported by our current observations, then the regions beyond our horizon should contain a similar density of galaxies to the one we see. If the total universe is indeed 250 times larger in diameter than the observable portion, its total volume would be a staggering 15 million times greater. This would mean that in the entire cosmos, there could be roughly 30,000 trillion galaxies. And if the universe is infinite, the number of galaxies would be infinite as well. These dimensions are, for the human mind, essentially impossible to fully grasp. We can write these numbers down on paper, we can use them in complex calculations, and we can build digital models to represent them. But to truly internalize what they mean on a deep emotional level is another matter entirely. We are like inhabitants of a tiny island, staring out at an endless, dark sea, knowing that beyond the curve of the horizon lie countless other islands that we will never set foot upon. However, the mere fact that we can recognize their existence is a profound triumph of the human spirit. Having contemplated the sheer quantity of galaxies, let us now zoom out even further to examine how these billions of worlds are arranged across space. Galaxies are not scattered randomly or spread evenly like grains of sand. Instead, they follow one of the most elegant structures in nature, the cosmic web. Astronomers have discovered that galaxies are organized along massive filaments that look like the delicate threads of a spider web. Where these threads cross, they form nodes, extremely dense regions, where thousands of galaxies gather together. Between these filaments lie vast, empty stretches of space known as voids, where galaxies are rarely found. This entire structure bears a striking resemblance to a sponge, the foam of soap bubbles, or even the neural network within a human brain. Let us explore this magnificent architecture starting from our own home. The Milky Way is by no means alone in the void. It belongs to a small community called the Local Group. This group consists of more than 80 galaxies, all bound to one another by the invisible tether of gravity. The 3 largest members are the Milky Way, Andromeda, and the Triangulum Galaxy. The remaining members are mostly tiny dwarf galaxies that orbit their larger neighbors like moons orbiting a planet. The Local Group spans approximately 10 million light-years, which is roughly 59 quadrillion miles. Even traveling at the speed of light, a journey from one side to the other would take 10 million years. Yet, when compared to the larger structures of the universe, our Local Group is minuscule. It is merely a small part of the much larger Virgo supercluster. This supercluster contains about 100 galaxy groups and clusters, including our own. At the heart of this structure lies the Virgo cluster, a dense concentration of more than 1,000 galaxies located about 54 million light-years away from us. The entire Virgo supercluster has a diameter of roughly 110 million light-years and is home to an estimated 100 trillion stars. But even this massive supercluster is not the largest structure we belong to. In the year 2014, astronomers announced the discovery of an even more colossal complex known as Laniakea. Laniakea is a giant supercluster system encompassing about 100,000 galaxies. It stretches across an impressive 520 million light-years, roughly 5 times the size of the Virgo supercluster. The Milky Way sits near the outer edge of Laniakea, in a relatively sparsely populated region, and Laniakea, in turn, is just one of the countless supercluster systems that together form the all-encompassing cosmic web. We have spoken of Laniakea and the giant superclusters that define our cosmic neighborhood, but the true skeleton of the universe is even more intricate and yet more powerful than we can imagine. The filaments of the cosmic web are the places where the vast majority of galaxies in the universe find their home. These filaments function like cosmic highways or great rivers composed of dark matter and gas, and along which galaxies have flowed for billions of years. A single one of these filaments can stretch across distances of hundreds of millions of light years. They are the lifeblood of the cosmos, connecting everything in a delicate, naive, invisible embrace. Where these giant filaments meet, nodes are created. These are the most densely populated regions of the entire universe. In these intersections, we find galaxy clusters, massive collections of hundreds or thousands of galaxies, bound by gravity and embedded in giant halos of dark matter and superheated gas. One of the most impressive locations is the Coma Cluster, which is located about 330 million light-years from us and houses more than 1,000 galaxies. Even more massive is the galaxy cluster Abell 2029. It is dominated by a single giant elliptical galaxy that contains over 100 trillion stars, a number that truly shatters our imagination. But between these glowing threads and busy nodes lie the voids, the yawning silences of outer space. However, these regions are not completely empty. There are worlds we call void galaxies, though they are extremely rare. In a void, the density of matter can drop to only 10% of the average density of the universe. Some of these empty spaces are of a terrifying size. The Boötes Void, discovered in the year 1981, measures about 330 million light-years in diameter and contains fewer than 60 galaxies. To give you some perspective, a region of this size in a normal part of the universe would typically house about 10,000 galaxies. Even larger is a giant void that stretches across 1,300,000,000 light-years. Imagine a sphere of almost empty space, over 1 billion light-years wide, where almost nothing exists. This entire network was created by the invisible influence of dark matter. Shortly after the Big Bang, matter was distributed almost evenly, but there were tiny fluctuations in density. Over billions of years, gravity amplified these differences. Dark matter, which makes up about 85% of all matter in the universe, formed the framework. It collapsed first into filaments and nodes, and then the ordinary matter, the atoms that make up stars. Planets and ourselves followed this call and flowed into the gravitational sinks that dark matter had already created. Despite this impressive architecture, most of it remains invisible to us. We have learned that the estimate of galaxies jumped from 100 billion to about 2 trillion, but the majority of them still escape our sight. Even with our strongest telescopes, we cannot capture them. Some are too far away, so their light has not yet reached us. Others are simply too small or emit too little light. The largest group of these hidden objects are the dwarf galaxies. They represent the overwhelming majority of all galaxies, yet they remain in the dark. Every telescope has a sensitivity limit, a threshold below which objects are too faint to be registered. This leads to a distortion in our catalogs in favor of large, bright galaxies, like the Milky Way or Andromeda. We see the glowing metropolises of the universe, but we overlook the tiny villages with only 1,000 stars. Astronomers use the term surface brightness to describe how strongly the light of a galaxy is distributed over its area. There are galaxies with extremely low surface brightness that spread their light so thinly in space that they become almost one with the blackness of the background. An extreme example of this are the ultra-diffuse galaxies. These can be as large in diameter as the Milky Way, but they contain so few stars that they act like cosmic ghosts, physically enormous, yet almost impossible to detect. The first of these ghosts were discovered as early as the year 1984 in the Virgo cluster, but they were ignored for decades because they were so difficult to study. It was not until the year 2015 that astronomers began to find them in large numbers. In the Coma cluster alone, over 800 of them have been identified. They could be one of the most common types of galaxies in the entire universe. All in all, this means that for every galaxy we can see in the sparkling night sky or on the recordings from Hubble, there are about 9 others that remain invisible to us. We are looking at an ocean and seeing only the brightest crests of the waves, while the depths are full of life and structures that we are only just beginning to guess exist. To truly grasp the hidden majority of the 2 trillion galaxies that inhabit our universe, we must move beyond the limitations of visible light. For centuries, we were like explorers, trying to map a vast continent using only a flickering candle. We could see what was right in front of us, but the true scale of the landscape remains swallowed by the shadows. One of the most significant categories of these hidden worlds consists of what astronomers call high redshift galaxies. As light travels across the unfathomable distances of an expanding universe, it undergoes a physical transformation. It is literally stretched, because the space through which the light travels is itself growing. The wavelength of that light becomes longer. This phenomenon causes the light to shift toward the red end of the electromagnetic spectrum, a process known as redshift. When we look at galaxies that are extremely far away, this shift is so dramatic that the light they originally emitted as visible or ultraviolet has been stretched entirely out of the range that human eyes or traditional optical telescopes can detect. It has moved into the infrared, because our eyes and most of our older instruments are blind to this part of the spectrum. These ancient galaxies remained invisible to us for decades.
We're losing the uplink on
This
the
is
main
precisely
screen.
why the James
Stabilize
Webb
the
Space
connection.
Telescope
I'm
was
bringing up
conceived
the
and
schematic.
built. Webb is not just a more powerful version of Hubble. It is a specialized machine optimized for infrared light, designed specifically to see the worlds that have been hidden by the expansion of the universe itself. Even in its earliest images, Webb began to reveal galaxies with red shifts that had never been observed before. Some of these distant flickers sent their light on its journey when the universe was only a few 100 million years old, representing less than 3% of its current age. These discoveries were nothing short of startling to the scientific community. Many of these infant galaxies appeared surprisingly bright and massive, existing much earlier than our previous models had predicted. It was a discovery that forced astronomers to fundamentally rethink their theories on how the first structures of the cosmos were born. However, distance and redshift are not the only obstacles in our cosmic census. There is also the matter of cosmic dust. In regions of the universe where stars are actively being born, there are enormous clouds of dust particles made of carbon and silicon. This dust acts as a thick cosmic fog that absorbs visible light and then re-emits that energy as infrared radiation. A galaxy shrouded in this dust might shine as brightly as 100 billion suns. Yet through a standard telescope, it would appear pale, ghostly, or even completely non-existent. It was only through the lens of infrared astronomy that we were finally able to identify these brilliant beacons and begin to understand the true scale of star formation occurring throughout the universe. There is one more barrier that keeps us from seeing the full count of 2 trillion galaxies, and it is much closer to home, the zone of avoidance. When we look out into the deep sky, we are forced to look through the thick, cluttered disk of our own Milky Way, toward the center of our galaxy. The density of stars and the massive clouds of dust are so overwhelming that they act as a physical wall, blocking our view of anything that lies beyond. For a long time, we simply did not know what was on the other side of our own home. It was only with the advent of modern radio telescopes that we could finally pierce this veil. These instruments can see through the dust of the Milky Way, and they have already discovered hundreds of previously unknown galaxies hiding directly behind our galactic center. When you combine all these factors, the extreme redshift of distant worlds, the faintness of dwarf galaxies, the obscuring clouds of cosmic dust, and the blockage of our own galaxy, you begin to see why the hidden population is so vast. When Christopher Consolis and his team arrived at the estimate of 2 trillion galaxies, they were performing a mathematical feat to capture these invisible masses. Their models suggest that roughly 90% of all galaxies in the observable universe are simply too faint or too obscured for our current technology to see directly. This leads to a haunting realization for every single galaxy we can admire through a telescope. There are 9 more waiting in the darkness, hoping to one day be discovered. Behind these monumental discoveries are machines of incredible precision. The Hubble Space Telescope, launched in the year 1990, revolutionized our view of the cosmos by operating from an orbit high above the distortion of Earth's atmosphere. Its famous deep-field images were only made possible because the telescope could stare at a tiny, empty-looking spot for days at a time, collecting every single individual photon that drifted its way. But as we have seen, Hubble had its limits, because it focused mainly on visible and ultraviolet light. That is where Webb has taken the lead. With a primary mirror measuring about 256 inches in diameter, nearly 3 times the size of Hubble's Webb can collect vastly more light and peer much deeper into the infrared past. To do this, Webb must operate at the second Lagrange point, about 1 million miles away from Earth, where temperatures drop to a bone-chilling minus 400 degrees Fahrenheit. This extreme cold is a necessity. If the telescope had any warmth of its own, it would interfere with the sensitive infrared detectors trying to catch the faint heat signatures of galaxies from the dawn of time. The results have been historical milestones. Webb is showing us an epoch where the universe was less than 400 million years old, capturing the very first galaxies ever formed. Yet, we must not forget the massive observatories here on the ground. While they lack the perfect clarity of space, their mirrors can be built to a much larger scale. Facilities like the Keck Observatory in Hawaii or the Very Large Telescope in Chile use adaptive optics to correct the shimmering of the atmosphere hundreds of times every second. They provide the detailed spectra that tell us what these distant galaxies are made of and how fast they are moving. Looking ahead, the future is even more promising. The European Extremely Large Telescope, scheduled for completion around the year 2028, will feature a mirror spanning 128 feet in diameter. It will become the largest optical telescope in the world, likely revealing galaxies that are currently beyond our wildest imagination. We are living in a golden age of discovery, where the invisible is finally becoming visible, one photon at a time. Up until now, we have largely looked at galaxies as statistical data points, vast numbers in a giant list that we count, categorize, and measure. But we must remember that each of these 2 trillion galaxies is a unique entity with its own distinct history, an individual structure, and characteristics that exist nowhere else in the cosmos. Let us take a moment to step away from the grand totals and appreciate the sheer individuality of these worlds, beginning with the place we call home, the Milky Way. Our Milky Way is classified as a barred spiral galaxy. This means that at its heart, it possesses a bar-shaped structure of stars that stretches across approximately 27,000 light-years. From the ends of this central bar, elegant spiral arms wind outward like a cosmic whirlpool. We have identified 4 primary arms and several smaller offshoots. Our own sun is located in one of these modest extensions, known as the Orion Arm, positioned about 26,000 light-years from the galactic center, roughly halfway to the edge of the disk. Deep within the core of the Milky Way dwells a sleeping giant, a supermassive black hole named Sagittarius A star. It contains the mass of about 4 million suns. While it is a terrifyingly massive object, it is actually quite peaceful and quiet when compared to the active hearts of other galaxies. If we look toward our nearest major neighbor, the Andromeda Galaxy, we see a sister spiral that is significantly more formidable than our own. While the Milky Way is home to a few hundred billion stars, Andromeda is estimated to contain a staggering 1 trillion suns. Its disk spans 220,000 light-years, which is more than double the diameter of the Milky Way. Andromeda also hosts a much more massive central black hole, estimated at 100 million times the mass of our Sun. Many models predict that, in the distant future, Andromeda and the Milky Way will collide, eventually merging through gravitational chaos to form a single massive elliptical galaxy. However, if we want to see a true monster among elliptical galaxies, we must look to M87, located 54 million light-years away at the heart of the Virgo cluster. This galaxy is truly gargantuan, containing several trillion stars, vastly more than anything in our local neighborhood. M87 gained worldwide fame in the year 2019, when its supermassive black hole became the first ever to be directly imaged. This object is almost impossible to comprehend, possessing 6.5 billion times the mass of the Sun. It powers a massive jet of matter that shoots thousands of light-years out into space, making M87 one of the strongest radio sources in the sky. In stark contrast, we find the Large Magellanic Cloud, a loyal companion to our own galaxy. It is an irregular galaxy without a clear, defined shape, likely because the gravity of the Milky Way has spent billions of years distorting it. Despite its chaotic appearance, it is a vibrant cradle for new life. Hosting the Tarantula Nebula, one of the most active star-forming regions in our entire local vicinity. It also provided us with one of the most important astronomical events of the 20th century, the supernova 1987A. the closest stellar explosion observed since the invention of the telescope. These are only 4 examples, but every single one of those 2 trillion galaxies has stories just like these to tell. Each has its own central black hole, its own history of collisions, and its own unique evolution. When we say there are 2 trillion galaxies, we are actually describing 2 trillion unique cosmic systems where no 2 are ever exactly the same. They are 2 trillion individual worlds waiting for their light to finally reach us after traveling for millions or even billions of years. The number of galaxies in our universe is not a static or fixed value. It is an ever-changing figure that, interestingly, tends to decrease over the long eons of cosmic time. This happens because galaxies are not isolated islands. They are dynamic systems that frequently merge. When 2 of these gargantuan structures drift near one another, the invisible tether of gravity pulls them into an inescapable embrace. They may dance around each other for millions of years, drawing closer with every orbital pass until they finally collide and melt into a single, larger galaxy. This process was far more common in the early crowded days of the universe. In fact, many of the magnificent galaxies we observe today are the direct result of numerous such historical collisions. Even our own Milky Way is a survivor and a conqueror. It has swallowed many smaller galaxies throughout its long history and is currently in the process of absorbing several dwarf neighbors. Right now, the Sagittarius dwarf galaxy is being physically torn apart by the immense gravitational pull of our home. However, a much more monumental encounter looms on the horizon. The Milky Way and the Andromeda Galaxy are currently hurtling toward each other at a speed of approximately 250,000 miles per hour. While older estimates predicted a certain collision in about 4.5 billion years, newer studies suggest the future is slightly more uncertain. Some modern models now calculate the probability of a direct merger in the near future at only about 2%, suggesting it could take 7 or 8 billion years if it happens at all. If they do eventually merge, the result will be a colossal new elliptical galaxy. While galaxies merge on a local level, something even more powerful is happening on a grander scale. Dark energy is driving the expansion of the universe at an accelerating rate, pushing galaxy clusters further apart. Eventually, these clusters will be carried beyond our cosmic horizon and disappear from our sight forever in about 100 billion years. Nearly every galaxy outside our local group will have vanished into the darkness. Future astronomers, if they exist then, might look up and mistakenly believe their galaxy is the entire universe, as all evidence of other worlds and the Big Bang will have slipped behind the unreachable horizon. With the knowledge that there are 2 trillion galaxies, an inevitable and haunting question arises: is there life out there in all those worlds? The honest truth is that we simply do not know. Within the Milky Way alone, there are likely more planets than there are stars. Estimates suggest our galaxy could hold 40 billion Earth-like planets residing in habitable zones. When you multiply that single figure by the 2 trillion galaxies in the observable universe, you reach a number of potentially habitable worlds that is truly staggering. Yet, we are met with the Fermi paradox: if life and intelligence are common, why haven't we found any evidence of other technological civilizations? Perhaps we are truly alone, or perhaps intelligence is a rare miracle. It is possible that civilizations inevitably destroy themselves before they can reach the stars. Or maybe the distances between these islands are simply too vast to bridge. So far, our calls into the deep have been met only with silence. We owe the very existence of these galaxies to a mysterious substance called dark matter. It makes up about 85% of all matter in the universe. Yet it emits no light and reflects nothing. We only know it exists because of its gravitational influence on everything we can see. Without dark matter, galaxies could never have formed. It created the original scaffolding of the early universe. While ordinary matter was pushed around by radiation, dark matter began to collapse into gravitational wells, creating the sinks into which atoms eventually fell to form the first stars. Today, every galaxy sits nestled within a massive halo of this dark matter. The Milky Way's halo extends about 1 million light-years, 10 times further than the visible disk of stars. When we count 2 trillion galaxies, we are essentially counting 2 trillion dark matter halos that were dense enough to birth stars. However, a mystery remains. We see far fewer dwarf galaxies than our models of dark matter predict. This is the missing satellite problem. It is possible that many of these dark halos contain no stars at all, remaining completely invisible to us. This suggests the true number of structures in the universe could be even higher than our count of glowing galaxies. What will be the ultimate fate of these 2 trillion worlds in the billions and trillions of years yet to come? The laws of physics tell a story of galactic evolution that ends in a gradual darkening and an increasing sense of isolation. In our immediate future, the local group will continue its slow gravitational dance. In approximately 7 or 8 billion years, the Milky Way and Andromeda will merge into a single massive elliptical galaxy that astronomers already playfully refer to as Milkdromeda. However, while we grow together on a local level, a more unsettling process is occurring. On the grandest scales, dark energy is driving the universe apart at an accelerating rate in about 100 billion years. Almost every galaxy outside of our immediate neighborhood will have slipped behind our cosmic horizon, becoming forever unreachable. Future observers would look up at a nearly empty sky and might falsely believe their single galaxy is the entire universe, as all evidence of other worlds will have vanished into the dark. On even longer timescales, the stars themselves will begin to die. The last generations will consume their remaining fuel, and after about 100 trillion years, even the longest-lived red dwarfs will finally go out. The universe will transform into a cold graveyard of cooling white dwarfs and black holes that slowly evaporate into nothingness. Yet, that remains in an unimaginably distant future. For us, it is a profound privilege to live in an era where the universe still sparkles with light and galaxies are visible across billions of light years. Every distant galaxy we observe today is a time capsule. The light from a galaxy 1 billion light years away left its stars when life on Earth consisted only of simple single-celled organisms. While that light traveled through the void, fish appeared in our oceans, dinosaurs rose and fell, and humans finally stood up to build telescopes. When those photons finally hit a detector today, they tell us a story that is billions of years old. We do not see the universe as it is, but as it was. This journey of human understanding has been remarkably short. As recently as the year 1920, most astronomers believed the Milky Way was the entire universe. It was only in the year 1923 that Edwin Hubble proved the existence of other island universes by measuring stars in Andromeda. In just over 100 years, our worldview has expanded from a single galaxy to an estimate of 2 trillion. There is a deep physical connection between us and these distant worlds. The atoms in your body were forged in the hearts of stars that exploded long ago. The calcium in your bones, the iron in your blood, and the oxygen you breathe all originated in those cosmic furnaces. You are made of stardust. You are the universe reflecting upon itself. We exist on a small planet, orbiting an ordinary star in an average galaxy among 2 trillion others. This knowledge is humbling, yet it testifies to the incredible power of the human spirit, which, despite its limitations, builds instruments to count the unfathomable. The night is quiet now. The staggering numbers of 2 trillion galaxies and 93 billion light-years can now rest. Somewhere out there, light is still streaming toward us. Photons that began their journey billions of years ago and may set a new data point in our understanding of the cosmos tomorrow. Let the immense scale of the universe feel comforting rather than overwhelming. The galaxies will continue to turn, and stars will be born and die while you drift towards sleep, safe and warm. In a universe operating by blind physical laws, you are a precious moment of consciousness. Sleep now under the light of 2 trillion galaxies and dream of spirals, filaments, and the light that outlasts time. Tomorrow, the wonder of the universe will still be there. Good night.